Hi folks, it's Dr. P. This video is all about overflow. What is it and why do we care? Overflow is a simple concept, but it's a pretty big deal. Overflow is just telling us whether or not the arithmetic operation we just carried out was successful or not. That's it. Now the complicated part of overflow is figuring out whether or not it happened. And that depends on the kind of math that we're doing: addition, subtraction, or multiplication. But first, I really want to give some more background to overflow. Specifically, where does it come from? Every computing device has a limit to how large a number it can store. Where does this limit come from? Some devices, especially of the type that we're going to build in this class, just have a hardware limitation. Maybe we're building a 4-bit adder, so we can only count so high with 4 bits. Even if we expand our hardware to be 8, 16, or even 32 bits, we still have a limit to the highest value that can be stored in that space. In one of our labs later in this semester, we'll build an unsigned adder that uses a 4-bit adder chip. So we just straight up can't process values larger than 15 due to this hardware limit. We wouldn't want to display incorrect values that would occur when a number larger than 15 would be the result. So we need to do some overflow checking and resetting, which is an important part of that lab circuit. Even more complicated devices, like my TI calculators, have a limit, which appears to be 9 times 10 to the 99. Anytime I try to get a larger number, I get an overflow error. The importance of overflow errors is this: my calculator does not want me to think that I have a correct answer, when really, whatever number it just tried to store in memory wasn't going to fit. The actual data that would have been stored is invalid. So it's really important to give an error message, or somehow prevent this faulty data from accidentally being used. Without an overflow check, something would have been stored to memory, but that something would not be the value that I would be expecting based on my previous calculations. Any subsequent math that I would do on my calculator would be wrong. So the importance of overflow checking is to prevent garbage data from being stored in memory and being subsequently used to perform some type of calculation or operation. Another important note that I need to make about overflow checking is that we need to find a way to check for overflows that a computer or some type of digital logic can detect. So when we build a digital logic device, we can't always be there to figure out whether or not the answer that it's giving us is valid or not. Therefore, we need to find some type of algorithmic way to detect for overflows independent of the human brain. So how we're going to be checking for overflows isn't just, hey, does it fit? Does it not fit? Based on looking at the result. The way we need to find an overflow is based on how could I actually wire up a circuit to make this determination. Now that we've established where overflow comes from and why it's important to find it, how do we know if there's an overflow in a calculation? First and foremost, we need to know the limit to our hardware. In digital systems, the limit comes from how many bits our system is. Then, how to check for overflow differs based on if we're working with unsigned, which is only positive, or signed, which is positive and negative numbers. This video focuses on using signed numbers only. First, we have addition. What are the different possible kinds of numbers that I can add together? I can add positive to positive, positive to negative, negative to positive, and negative to negative. When adding two positive numbers together, I expect a positive result. Therefore, a negative result would be indicative of an overflow. In fact, if I add two positive numbers together and get a negative result, it's because an overflow occurred. When adding two negative numbers together, I expect a negative result. Therefore, a positive result would be indicative of an overflow. In fact, if I add two negative numbers together and get a positive result, it's because an overflow occurred. When adding a positive and negative number together, it's impossible for the magnitude of the result to be any larger than either one of the two inputs. Therefore, it is not possible to overflow when we add positive to negative or negative to positive. I just want to emphasize, overflows in signed addition has nothing to do with carries and everything to do with sign. A common misconception that my students have is that if there's a carryout on the last term, that overflow occurred. That is not how we check for overflow in signed addition, so don't do it! Next up, we have subtraction. Again, I can subtract positive from positive, positive from negative, negative from positive, and negative from negative. When subtracting a positive number from a negative number, I should always have a negative result. Therefore, a positive result would indicate an overflow. Negative minus positive equals positive means that an overflow happened. Similarly, when subtracting a negative number from a positive number, I should always have a positive result. Therefore, a negative result means overflow. Positive minus negative equals negative means overflow. When subtracting a positive from a positive or negative from a negative, it's impossible for the magnitude of the result to be larger than either one of the two inputs. Therefore, it's impossible to overflow in either of those two situations. Lastly, we have multiplication. Multiplication is weird because it's really hard to do in hardware. Whenever we multiply, we have to double the number of bits we use, at least temporarily. These extra bits are called overflow bits. After we do the multiplication, we use our overflow bits to check for the overflow, hence the name. All of the overflow bits must agree unanimously, so they must all be exactly the same. Not only that, but they must agree with the sign bit. If 100% of the overflow bits are the same, and they're also the same as the sign bit, then no overflow occurred. Otherwise, there was an overflow. When doing arithmetic in binary, feel free to smell check your answers. What I mean is, ask yourself what number can be stored in the number of bits you're limited to. Then ask yourself if the value that you expect to get from your arithmetic operations is going to be within that constraint. As always, keep practicing to feel more comfortable with overflow and understanding when and where and why it happens. Until next time, stay well.